Well, I manage the various research projects, the terrestrial research projects that we have at Blockstream. So basically everything except for the satellite, which Adam was talking about. And what I'd like to talk about here are a collection of research projects that we've been doing that center around Bitcoin, and that center in particular around something called Taproot. And this is a new technology that was proposed. We sent a draft describing this to the Bitcoin development mailing list a couple of days ago. Peter Willa at Blockstream sent this. And it's a proposal for an extension to Bitcoin that enables a whole wide cluster of things, in particular around doing smart contracting applications in a private and much more scalable way, or much more private, scalable. This has moved the much to private there. So let me start by defining a couple of terms. I've been using this word smart contract, and this is really a buzzword. It means a different thing to everybody else. So let me give a very concrete definition here, which is that a smart contract is a blockchain-enforced transfer of assets between some counterparties. Okay? And here I'm emphasizing that the blockchain is enforcing that this is happening. As we'll see, that's a bit more subtle than what a lot of people think about when they think about using a blockchain. This is not necessarily running code in a decentralized manner or anything. This is just ultimately somehow people agree that the assets should move. The blockchain steps in and makes sure that the assets actually do in fact move. Okay? And also, I'm assuming we have a fixed set of counterparties here. This is much more like a traditional contract. Sometimes people talk about things like the DAO and these really elaborate, like autonomous, decentralized objects and stuff. And these are a very different beast from the kind of things that I want to focus on here. Okay? So in all of this, there's kind of a trade-off that needs to be made when you're using a blockchain between privacy and confidentiality and the fact that a blockchain is a public store of data. If you put anything on a blockchain, then you need to publish it. Meaning that if you have a complicated contract with complicated conditions for moving assets, then you need to reveal that to the entire world if you're going to try to use a blockchain to do it. Or at least that's the way things have typically worked today. So with that in mind, maybe you might ask, like, why are we even using a blockchain? And the reason is that the blockchain provides a global, immutable view of the state of all coins and which coins are moving and at what times, and all of that good stuff. Okay? So before I get into what Taproot is and how that changes the face of these style of smart contracts, let me make a quick interlude and talk about something called compact multi-signatures. So this, it would be helpful to have slides here, but I'm going to try to hand talk my way through this. So compact multi-signatures, well, first let me define a digital signature. A digital signature is an object which is associated to some public key, which somebody has. It's a signature on a message that anybody can verify given this person's public key. Anybody can tell that this person actually signed it. But the only person who can produce it is a holder of an associated key called a private key. We are here. So in Bitcoin, to produce a multi-signature, meaning a signature that requires many participants, and this is not necessarily, this may be something like all of a set of participants. It might be what's called a threshold signature, where you have like 3 of 5 participants or 2 of 3. These are very common in things like escrow contracts and split custody wallets, things like Blockstream's Green. Also companies like BitGo or Casa are doing similar things. And right now in Bitcoin, to do these kind of multi-signatures, you need to just produce a separate signature. Everybody produces their own signature. You put them all in a row on the blockchain, and there they are. Everybody can see them. Okay? So that kind of sucks for 2 reasons. One is scalability. Verifiers need to download a signature from every single participant. They need to verify a signature from every participant. The existing signatures in Bitcoin, you can't even batch verify. You just have to do it one after the other. It's not very efficient. And then the second reason this sucks is because of privacy. Because you were revealing to the blockchain, and here's how many signatures are required. Here's the individual signers that have to produce those signatures. Here's how many of them need to sign. All that good stuff is just sitting out there. So there is a different style of signature than the one Bitcoin uses. Bitcoin uses ECGSA. There's another type of signature called Schnorr. Schnorr signatures have the property that you can jointly produce a Schnorr signature. Multiple parties, or even a threshold, you can set up a like 3 of 5 public key, come together and they jointly produce a single public key that represents all of them. And in order to produce a signature, those participants, either all of them or whatever threshold many, interactively communicate with each other, and very efficiently they are able to produce a single signature with this joint public key. And so what hits the blockchain is a single public key and this single signature. So nobody sees what the original keys were going into this. Nobody sees what the threshold is. You can even have multiple thresholds. You can do more elaborate things. You can have like any sort of tree of policies. You can say 3 of these 5 or 2 of these 3 or something else like that. And the result is just a single signature. So we get our privacy benefits. We also get our scalability benefits because now it's just one signature. Okay? So what Taproot is a proposal for Bitcoin in which all Bitcoin outputs, all coins that are available to be spent, use these single signatures by default. So right now, Bitcoin has something called Bitcoin Script, which is this elaborate scripting language that lets you do all these cool things I've been talking about. Where rather than having a script associated to every single coin that needs to be satisfied, we just have a single key and a single signature. And using something like Musig, that single signature is able to represent more complicated policies. And in particular, thresholds, multi-signatures and stuff. And then as we'll see, there's even more we can do with single signatures beyond just multi-signatures. But it can't do everything. It's not possible to do everything with signatures. There are good reasons that Bitcoin Script exists, and there are good reasons that it's used. For example, there are sometimes time-locked conditions on spending coins. So there's this primitive called claim or refund that's used in a lot of smart contracting protocols, where somebody has to put up coins initially. They put them into some sort of multi-signature output. And then they interact with their counterparty, executing the terms of whatever contract they're doing. But if one party disappears and the contract can't complete, the person who puts up the coins needs to know that after some period of inactivity, they can claw back their coins. Okay? So what Taproot does is it hides a Bitcoin script inside of the public key. That's sort of this cryptographic construction where you can take a key, just an ordinary signing key that may represent multiple parties. You can hide a commitment to some extra auxiliary data in there, and you produce a tweaked key with another key, but it still looks like an ordinary key. And the idea here is that if people want to sign by producing a signature or a multi-signature or whatever, they can just use the key, and they're off to the races. And if they can't do that for whatever reason, maybe they need to have some time-locked extra conditions or some alternate or something like that, then they can reveal this extra script that they committed inside of their key. Blockchain verifiers can see that this commitment is valid and it's actually part of the key. And then they can use that instead. So the idea here, the privacy upshot here, is that in the cooperative case, in the normal, typical case, for basically everything people are using Bitcoin for, this includes normal, like people sending coins to each other and to businesses and stuff. This includes 2 or 3 threshold payments, escrow payments, stuff like this. As we'll see, it can include things like the Lightning Network, which my colleague Christian talked about yesterday. And assuming nothing goes wrong and you don't need to use these backup, like refund time lock conditions, you never reveal that there are any complicated conditions in there. All outputs look the same, no matter what they are. Okay? So, Taproot is, Schnorr signatures are a buzzword as well. And what I'm going to try to do in this talk is try to replace the word Schnorr signatures, which also means different things to different people. This appears in the press a lot. Schnorr signatures will make Bitcoin more efficient. It will make it more private. It will make transactions be combinable. It will make like everyone happy. These are all wonderful. And unfortunately, there are many different things that you can do with Schnorr signatures, and not all of them come together at the same time. So Taproot is a specific, concrete proposal. It's exactly the proposal I described, where we we allow users to put their coins into public keys that have scripts hidden in them, and then maybe spend them in various ways. The embedded script in Taproot is not quite Bitcoin script. I talked about Bitcoin script, but actually it's a slight extension of Bitcoin script that has 3 major differences. One is that we've replaced ECDSA signatures that today's Bitcoin script knows how to validate with Schnorr signatures. And the reason for that is that we can use musig to produce multi-signatures and threshold signatures. It also extends what are called the sighash flags in Bitcoin. These are flags you can set on your signatures that control which parts of your transactions you sign. And the reason you might not sign an entire transaction is to allow counterparties to extend your transactions in certain ways while still ensuring that you've signed the parts of the transaction you care about. We've extended those flags to support some new use cases and to support some extensions to the Lightning Network. And then finally, it includes something called MAST, Merkleized Abstract Syntax Trees. And what this is a mechanism by which you can take all of your different conditions for spending. And rather than writing a script that requires a user like put a 0 or 1 into there and like flips a coin, chooses which branch is going on, and everybody sees this chain of like, if there's a 0, then use these conditions. Otherwise, if there's a 1, use these conditions. Otherwise, if there's a 2, use these conditions, and so on. That's typically how you write scripts in Bitcoin today. It's just like you write every single condition, and you have explicit, some way of choosing between them. What MAST does is it just hides them all. You have what's called a Merkle tree, which is a way of committing to many different things at once in a way that is possible to efficiently reveal one while hiding the others. And this also gives us both a privacy and a scalability benefit because we are no longer revealing script branches that in practice are not used. Right? When you actually spend a coin, you only use one branch. So why does everybody need to see all these other branches? Why do they need to download them? Why do they need to parse them and make sure that they're valid scripts? All of that stuff seems unnecessary. So MAST lets us just hide those. You have a giant tree of all your different spending conditions, and you reveal the one that you use. And as we'll see, almost all of our branches are unused. So what I've talked about so far is that if we take the top level branch, which is really a public key with a commitment to a root of all the other branches hidden inside, if we just use that, we're able to do multi-signatures and threshold signatures using musig. And the underlying assumption behind this is that if you have a set of counterparties trying to execute a smart contract, and they all agree that the conditions of that contract are satisfied, then they can just go ahead and come together and sign to move the coins. There's actually no need to use a blockchain for anything as long as all counterparties to the contract agree on this, right? That's the intuition. This is what's called the Taproot Assumption, and that's why we designed this to privilege the multi-signature spending policy versus any of the other kind of things that people use script for. But this is not quite enough in all cases. So there are many different contracts that people use, such as atomic swaps between blockchains, or the Lightning Network, where you have a series of atomic payments connecting off of each other so you can like forward funds through some long path of people, where cooperation is not quite enough. Because what's happening at the center of these contracts is that somebody is trading information for money with somebody else. And when you're trading information, typically you're revealing the pre-image to a hash or some secret like this. Then somebody has to go first, right? Either you send the coins and your counterparty might not give you the information, or your counterparty gives you this information and you just walk away, right? And the way that this is circumvented, this problem of who goes first is circumvented in Bitcoin and in Ethereum and pretty much everywhere else today, is that you create a contract using something like Bitcoin script that says the coins are not allowed to move unless somebody signs and somebody reveals the pre-image to a specific hash. So you take your secret, you run it through SHA-2 or some hash function that doesn't reveal the secret at all, and you publish that as part of your contract. And then when you're spending the coins, it forces you to reveal the pre-image. And so this way, the coins can't move without both the signature and the pre-image. So you get this atomicity of the swap, which is great except for we're revealing the hash, we're revealing the pre-image to the entire world on the blockchain. This sucks for the usual privacy and scalability reasons. If you're doing something like Lightning, where you are chaining multiple payments through each other, you actually have to use the same secret at every single step of the way. So there's an even further privacy hit, where if you have a Lightning payment going through like 10 hops, all these 10 hops are going to have these transactions with the same hash, the same pre-image. So now you're not only revealing that you're using Lightning and that you're using this particular pre-image, you're revealing the linkage between all of these payments, which in principle shouldn't be linked. Right? They're atomic with each other, but they're ultimately independent payments, independent payment channels being updated just in a way that they get updated at the same time. So there is a way around this using something called scriptless scripts. The scriptless scripts is also like a wide blanket of different research initiatives, but there are two in particular that I'm going to focus on. Actually, there are two that I'll mention, just one that I'm going to focus on. One is something called adaptive signatures, which let us do exactly this secret exchange that I just described. And the other is something called discrete log contracts that were developed by Taj Draya at the MIT Digital Currency Initiative that let you do some other more interesting things. It lets you input Oracle inputs like assigned price data or time data or weather data or insurance contract, whatever real-world data you need to input, you can use these discrete log contracts to sneak these into signatures. But I'm not going to talk about that. I'm going to talk about adaptive signatures, because those let us do Lightning, those let us do atomic swaps, those let us do a whole pile of cool things. So the way that an adaptive signature works is that, this next slide. No, OK. The way that an adaptive signature works is that when two participants are jointly producing a Schnorr signature, like using Musig to put these signatures together, and one party does not want the signature to complete and the coins to move unless they learn some data from the other party. This is our classic atomic swap. This is used in Lightning. It's used in atomic swaps. This classic trading information for coins, trading information for signatures problem. What adaptive signatures do is the party who is providing the secret information thinks up this information, and rather than giving their contribution to the multi-signature, they are going to encrypt their data to their contribution. Or equivalently, these are actually mathematically equivalent, they're going to encrypt their signature to the data. They just kind of mix them in a symmetric way. And they give that information out. They publish it, or actually they don't even need to publish it. They just send it to whoever they're signing with. And now the other party is then able to sign to move the coins. And the reason is that they know that as soon as the party with the secret makes their signature, they will have to, or makes their contribution to the signature, to actually execute the contract, to actually move the coins, they will need to publish a signature to the blockchain. And so the way this all shakes out is the party with the secret encrypts their secret to their signature. The other party contributes part to the signature. The first party reveals their contribution to the signature by creating that, combining it with the first party's thing, now it's a complete signature, publishing it to the blockchain and moving the coins. So what happens to the person trying to get this information? Well, they look at the blockchain. They see a signature has appeared. They see that their money has disappeared. They take that signature. They subtract their own contribution from it to get the counterparty's contribution. They subtract the encrypted version of the secret from the other party's contribution, and they are left with the secret itself. So the signature now actually contains an encrypted secret. And so in this way, these two parties are able to trade signatures for information in a way that nothing is revealed to the blockchain about what that secret is. What hits the blockchain is just a single signature. In fact, nothing is revealed to the blockchain that indicating that there are multiple parties involved. This looks like a normal single person sending coins kind of thing. But in the background, these counterparties have interactively produced this signature in a way that they can be assured that they have exchanged this information for some sort of asset flow in a way that nobody has to trust anybody. Nobody has to go first. Okay? And so this means that accepting these time-locked emergency refund things, everything that's used in Lightning and in atomic swaps and in something called zero-knowledge contingent payments that I'll talk about in a moment, but I don't want to distract from this, can be done in a single Schnorr signature. Okay? And to emphasize, I'm trying to get these terms clearly separated. The Schnorr signature is just a specific signature that hits a blockchain. Taproot is a set of rules surrounding that describe in what context Schnorr signatures are validated, when they have to be produced. And then Musig is this interactive protocol that people use to jointly produce a single Schnorr signature. Okay? So this is pretty cool. This is basically all of the uses of the Bitcoin blockchain. This is the escrow payments that people are doing, using 2 of 3 threshold signatures. This is things like atomic swaps. This is the Lightning Network. This is Blockstream's Liquid, which uses an 11 of 15 multi-signature to control custody of all of the coins in the system. This is two-factor wallets. This is non-custodial wallets. This is all sorts of cool stuff. All come down to a single public key that indicates the control of the coins and a single signature that's used to spend them. Okay? And this is back when I started this talk, when I talked about blockchain-enforced smart contracts. Here's like really the upshot of this. The blockchain is making sure that the coins don't move unless the people who have an interest in those coins agree that they move. The blockchain does not care about the details of that. They don't know what those specific interests are. They don't know what conditions people need to make sure the coins move. They don't need to know how many people are involved or how many people might be involved or anything like that. All they need to know is that whoever had interest in the coins agreed that they should move. And they do so by verifying a digital signature, which can only be produced, assuming everybody's working according to the protocol, can only be produced by correct execution of this contract. And with Taproot, we always have this hidden script in the background. So if things go wrong, if somehow people aren't following the protocol, if they're disappearing or giving bad data or screwing around somehow, then you can always reveal some backup script that is explicitly enforced by the blockchain, because apparently the parties can't enforce it on each other. And they reveal that script, they use that, everything's good. So there is no risk to safety in doing this. So in the cooperative case, you have privacy and scalability. In the non-cooperative case, you still have safety. And the result is that you have all of these coins, all these different applications whose coins look indistinguishable from each other. So you also achieve much better fungibility for the currency for Bitcoin than you have today, because nobody can tell which coins are owned by individuals, which coins are owned by quorums of signers, which coins are currently embedded in some complicated ongoing contract. All of that stuff kind of looks the same. Okay? So, in summary, and to briefly introduce zero-knowledge contingent payments, we have this thing called scriptless scripts. Lets us hide all these cool things inside of signatures. Okay, that's great. That's what I just described. There's another application of adaptive signatures, which I will quickly describe, that I want to bring up to emphasize how powerful this is. I talked about how to do swaps in the Lightning Network, but you can do much more than this. So I talked about trading signatures for secrets. And in the Lightning Network and in atomic swaps, what you do with this secret is you just turn around and turn it into another signature to make different transactions atomic with each other. You just have different transactions that depend on the same secret. So, I mean, it's not really meaningful in itself. It's just some random data. If you know it, you can sign a bunch of transactions. To sign one, you have to reveal it, thereby enabling to sign them all. That's atomicity. Okay? But there's another much more general application, which is the party who has the secret could instead have some other problem that they've solved, some more interesting, meaningful information than some random secret that they want to reveal. There's kind of a proof of concept thing implemented where one party wants to sell a Sudoku solution to the other. But you can imagine more elaborate things. You can imagine a party's trying to prove that they got a signature from some oracle or something, authorizing some transfer. They might want to prove that, that they have an attestation to something interesting they discovered, like the location of oil in some satellite image, or something elaborate like that. You can imagine basically any problem that has a computationally verifiable solution. It is possible to trade that solution for coins using this mechanism. And here's how you do it. You take your 32-byte, your little random secret that is actually what adaptive signatures allow you to trade. What you do as a holder of the secret is you take your big, crazy, elaborate structured secret. You encrypt that to the first secret. You use that as like an AES key or something. So you have this giant blob of encrypted data. And then you produce something called a zero-knowledge proof, proving that actually you solved the problem, you put the problem in some encoding, you AES encrypted it with some key, and that key is the one that you're going to trade for the signature. So there's this construction called zero-knowledge proofs floating out there that let you prove dramatic statements like this without revealing anything about what you actually put into that proof, about the actual data. And so once you do this, you then do this atomic swap construction, this signature for secrets construction. You sell the secret to some counterparty. The counterparty knows when they learn that secret, it will enable them to decrypt this elaborate solution. And they know that that is actually a solution to whatever problem they might have. So up to the scalability and efficiency properties of these zero-knowledge proof constructions, you can do pretty much anything that you could do with a smart contract using this construction by saying, I satisfy these conditions. Here's a computational proof that I did this. Here's an encryption of that proof. It's all zero knowledge. I'm not revealing it, but I will reveal the encryption key if you give me my money, kind of thing. And then finally, just to reiterate, Taproot is a proposal for Bitcoin which will enable scriptless scripts, will enable all of these elaborate things, and do so in a way that essentially all these different applications will look the same when they land on the blockchain. And that's all I've got for you. Thank you.